Okay guys, let's talk about rectified linear unit, ReLU and leaky ReLU. These are very important activation functions used in modern deep learning networks, okay? Now, what's the activation function? What's the role of the activation function? Essentially, you want to turn the neuron's pre-activation value z, which is a linear function of the previous neurons. Now you want to take that pre-activation value into one output, which is a is equal to fz. And this activation function is usually nonlinear. If this itself was linear, then you would really have a bunch of linear functions, linear functions, which would essentially collapse into one linear transformation, which really wouldn't be very useful. So you do need it to be nonlinear to make the entire deep learning network possible. Now, one of the most common activation function is the sigmoid. A specific case of sigmoid is the logistic function. Many times people think of it together. Watch the separate video on it, the previous one that has been published on this topic, which is essentially talks about the sigmoid. Sigma of x is equal to 1 divided by 1, the entire thing, 1 plus e power minus of x. Okay, it can also be written as sigma x over 1 plus sigma x. And the good thing about the sigmoid function is that it maps any real valued number to a 0-1 range. It's super useful, especially when you're talking about trying to map a value into probability 0-1. Think of a binary classification problem. And this was the actual first commonly used activation function. Just to talk about one quick property of the sigmoid function, think about the derivative. The derivative of that sigmoid prime can be written as sigmoid of x 1 times sigmoid of x. And again, this is some simple math that you can use to derive some of these key properties here. So the sigma of x varies all the way from 0 to 1. Sigma prime x will max out at 0.25. Okay. In many cases, sigma prime x, that means the derivative will be 0, especially when x is very low or very high. X only around x is equal to 0, sigma prime x is substantive, it's substantial, where specifically for x is equal to 0, you have sigma prime x maxing out. Okay, so it's 0 for a lot of x values. Now, what's the vanishing gradient problem? That is really the root of why we use ReLUs now. So in deep learning networks, deep networks, gradients are multiplied layer after layer when you're thinking about the back of the descent algorithms. So if each sigmoid layer contributes a factor which could really be from very low, like 0, even maximum value of 0.25, even after 10 layers, your gradient is going to be really small. In many cases, it's going to be very near 0. So therefore, the learning signal just becomes really tiny before it reaches the earlier layers, starting from the end layer. And that is really the problem with the sigmoid function for the deep learning networks. And when the z is very high or very low, sigmoid is essentially just flat. That means sigma prime is equal to 0. Okay. So if many neurons are sitting in the saturated state, your backpropagation isn't really doing much at all. What's the ReLU function, the rectified linear unit? It just borrows from the electrical engineering concept of rectifier. That means everything that's negative, set it to 0. Okay. And that's really what it is. So it's written as maximum of 0 or z. So if z is positive, it's z. If z is negative, it's 0. That's it. It's a rectified linear unit. It's essentially just a linear function, the identity function f of is equal to x, except when x is negative, then it returns 0. That's it. It is just super simple. It's piecewise linear, and just, of course, it's super easy to compute. There's no e power, there is no log, there is no tan, none of that business there. Now, why does the rectified linear unit help? Well, the reason it helps is it's a linear function, at least in the positive cases, right? So in the positive cases, when it's a linear function, that means its derivative is 1. F of x is equal to x. Think of the positive side. F prime x is equal to 1. Therefore, backpropagation, the the gradient descent is actually getting multiplied by 1. Therefore, the vanishing gradient problem actually vanishes itself. So that's one of the main historical reasons that the ReLU became dominant in deep learning for the intermediate layers, even though the more complicated function, the sigmoid function, came prior to ReLU. So that's the interesting aspect of it. Now, ReLU also creates sparsity. What does that mean? That if, for example, many of the neurons for which you have z is less than or equal to 0, ReLU output is 0, therefore your overall function will become minimal. So that does make activations sparse, and the activations are essentially make the representations simpler, more minimalistic, and they reduce unnecessary computations as well in some settings. So that's also one significant advantage of ReLU. Now the cost of ReLU though is that if you have if the value is negative, you will have the z will always be negative, so the output's always 0. So therefore the ReLU prime is equal to 0 for all training examples. Therefore, the neuron may stop learning entirely. Then you have a dead ReLU, also called the dead neuron in this case here. To fix that, we have a slightly different version of it, which is called the leaky ReLU. So again, borrowing from the electrical engineering concept, we could have a rectification. It's rectified linear unit, except it does leak a slightly negative current back. So this is written as leaky ReLU is equal to maximum of alpha x comma x. So if alpha is a very small value, like let's suppose 0.01, so if x is greater than 0, then leaky ReLU is just equal to x. If x is negative, such as -1, then we'll multiply that with 0.01. So 1 becomes negative, minus 1 becomes minus 0.01. So it just has a small slope. It doesn't rectify it entirely just to 0. That's basically leaky ReLU. So why is it useful? Exactly like we discussed, ReLU will have dead neurons. Leaky ReLU will prevent that problem. Now, of course, it's also nothing like sigmoid, so there is no complication, no computation to do that as well. There's a near linear gradient flow for positive, exactly like we discussed. It's a simple computation, but it does reduce the risk of dead neurons. So here's your quick comparison. Sigmoid, the earlier function, sigma of x, e power x divided by 1 plus e power x. ReLU, which is just basically just x if x is positive, otherwise 0. And leaky ReLU, which is kind of like ReLU, but for the negative value, it'll multiply that with 0.01, so slope becomes a little bit less. So that's the takeaway. Now, sigmoid is still very, very, very useful, especially in the final layer of something like a binary classification. It's a smooth function, it's differentiable, it really can be used at all. It has the entire domain, x from minus infinity to infinity. The output is from 0 to 1. ReLU, of course, the range is from 0 to infinity. And leaky ReLU from minus infinity to infinity, but it has a negative slope that's very, very, very small. It's a small modification that helps prevent dead neurons, but ReLU is itself, again, in a one-step takeaway is that ReLU is much better than sigmoid for the intermediate layers because of the gradient descent, that you won't multiply it with 0.1 or 0.25 in the best case, which after 20 layers, after 30 layers, after 40 layers, it would essentially be non-learning. So there you have it. That's your leaky ReLU and leaky ReLU, and you have your entire activation function here.